right. Hi there. Welcome, everybody. I wanted to put together a brief supplemental video to some of the things that we have been talking about in class on Tuesday nights in Physics 10. Wanted to go over in a little bit more detail the two competing models of the universe that later thinkers like Copernicus and Galileo, Kepler, Newton were going to be arguing out and trying to eventually succeed in making the case that the second model I'm going to tell you about, the heliocentric model, is by far a better fit to the data than the geocentric model. Now, what did I mean by the geocentric model? The name kind of gives it away. Geocentric, geo means the Earth, centric just means centered. So this was Aristotle's old model of, and I was going to say old model of the solar system, but it was actually what he was proposing was a model for the entire universe. He thought he had successfully mapped out how the entire universe is structured. The entire universe might seem pretty ambitious for one of the first systematic thinkers on these issues, except that he did not think the entire universe was nearly as big as we know that it is today. Essentially, they had a very cozy model of the universe in the ancient Greek and Egyptian civilizations. They thought that the most distant possible objects, which would be what they called the fixed stars, were only maybe 2 or 3 times as far away as the sun was. And as I've told you, at some point fairly early on in the history of this model, with the work of Eratosthenes and Aristarchus, they were able to measure how far away the sun was. They got it wrong by a factor of 10, but at least they were able to kind of get a ballpark thing of how far away the sun was. So again, they thought they had the size scale worked out for the entire universe. Now, how did they think the universe was structured? Well, as I told you in class, Aristotle was strongly convinced that the Earth, the ball, and he wouldn't have called it the Earth. He would just called it the world or something like that, because Earth was the name of the element that meant solid matter. But the world that we're standing on, what we now call the Earth, he would say it's well, Aristotle knew it was a sphere. Credit to him there. He did not yet know how big it was, although he kind of had a ballpark estimate, and Eratosthenes would very successfully measure the size of that sphere to be 25,000 miles in circumference. But he said it's a sphere of solid rock. It's at rest at the center of the universe. Now, again, when he said the center of the universe, this was not so much that he thought this ball of rock we're standing on is the most important object in the universe, but he thought there was a geometric point at the center of the universe, and that's the most important geometric point anywhere. That's the center that all of physical reality is built around, including the fact that this ball of rock that we happen to stand on is clustered around that center of the universe. Now, today we would say the Earth that we're standing on, the world that we're standing on, rotates every 24 hours on its own axis. Aristotle considered that possibility because he was well aware that if you look up to the sky, everything that you see wheels through the sky every 24 hours. And yeah, one possible explanation for that is it's not the sky that's moving, it's me. If I rotate every 24 hours, I would see literally everything in this room coming into view on the left side of my field of vision, crossing my field of vision, and kind of setting out of sight on the right side repeatedly again and again. Well, that's what we see when we look at the sky. The moon, the sun, the stars, the planets. We see all of these things rising in the east, wheeling across the sky, setting in the west once every 24 hours. Again, to Aristotle's credit, he was aware that one possible explanation for this pattern is that the world that we're on is rotating every 24 hours. And he rejected that idea. He rejected the idea because he thought we should feel the world moving if it was spinning, and calculated that, roughly we would be moving like 1,000 miles an hour toward the eastern horizon. Wouldn't we feel that motion? The answer would turn out to be no, but this was because Aristotle was not just wrong about astronomy, he was fundamentally wrong about physics. And that's a discussion that I'll shelve until next Tuesday's lecture, and then we'll take that up and run with that strongly. But he rejected the idea that the Earth was rotating, which means that he thought that instead the entire cosmos rotates every 24 hours. Everything in the sky. He thought of it as a giant machine, and you could imagine there's an axle running through the center of the machine, kind of perpendicular to the board in this case. And the whole thing is, it would be turning this way. The Earth's actually rotating the other way. If I'm looking down on the North Pole, the Earth's actually rotating the other way. It's rotating counterclockwise. But if you're ignoring the Earth's rotation and thinking it's the sky that rotates, you think the sky would be rotating clockwise if you're looking down from the North Pole. So this would be the rotation every 24 hours of this entire celestial apparatus, this entire machine. Now, for some of the lights, which he, again, as we explained in class, defined to be spheres of ether, that quintessential fifth element that he liked so much. But for some of these celestial objects, the only thing they do is rotate every 24 hours. Those fixed stars out there, which Aristotle considered the farthest away objects there are, and you can say, yeah, we do consider the stars the farthest away objects they are. That's not a mistake. Well, no, but we think that, yeah, we know, we've measured that the stars are vastly distant. He thought they were, again, maybe 2 or 3 times as far away as the sun. But the stars, the only motion you would catch them doing was that 24-hour cycle as the entire cosmos rotated. But most of the other objects in the sky had their own rotations on top of that. The moon, they calculated, orbits the Earth roughly every 28 days. The sun orbits the Earth also, but much more slowly, every 365 days. You may recognize that as roughly the length of the lunar month and the length of the year. How did they know that these objects were orbiting the Earth and were not, in addition to their 24-hour rise and set cycle? Because you could keep track of where they are silhouetted against the fixed stars, and the answer to that would change with time. Again, every 28 days roughly, the moon would do one orbit around the Earth, and you could tell because it made a complete circuit against that background of fixed stars. The sun made a complete slower circuit. It took it 365 days to make a complete circuit against the background of fixed stars, and again, finish an orbit around the Earth. Now, the sun's not really orbiting around the Earth, it's the other way around, but they thought the sun was orbiting around the Earth. That's how they interpreted those measurements. Now, the 5 planets, why only 5 planets and not 8 or not 9 if we're still counting Pluto? Because again, as we talked in class, they didn't consider the Earth a planet. It was a separate type of object. The planets were these balls of ether in the sky. The world that we're on is a ball of solid rock. It's a completely different and humbler kind of object. Still, why does the count as low as 5? Because some of the planets, particularly Neptune, Uranus, and Pluto, if you consider Pluto a planet, are faint enough and distant enough that you can't see them with the unaided eye. We would need better instruments such as telescopes to discover those. So what were the planets they were aware of? I've only drawn a couple of them up here because I didn't want to make the model too crowded. But the planets they were aware of, kind of from the closest to the sun to the farthest, were Mercury, Venus, Mars, Jupiter, and Saturn. Aristotle originally kind of had no real place in his model for the planets. They were just kind of weird nonconformists that they were doing their own thing. They seemed to be wandering randomly through the skies. Again, that might be one reason why they named them after the Greek and later the Roman gods, is because they seemed to be these capricious figures from folklore that nobody could tell them what to do. They just moved where they wanted to move. However, Ptolemy's adjustment to this model. Now, Ptolemy was an Egyptian astronomer. That's the spelling of his name there. There was a pharaoh named Ptolemy at the same time. This was not Ptolemy, the king of Egypt, if you've studied them both in history class or anything like this. This was the much more humble, but probably much more talented man, Ptolemy the astronomer. But where was he in history compared to Aristotle? He was about 500 years later. Aristotle had been at the height of his career around BC 350. Ptolemy was doing his best work around AD 150. So subtract the numbers, that's about 500 years. So quite some time had passed before you got a serious update to Aristotle's model. What Ptolemy's update was he made a systematic study of how the planets behaved. And he found that although it had seemed at first that if, at a casual study, those 5 planets, Mercury, Venus, Mars, Jupiter, and Saturn, seem to be just wheeling on random trajectories through the sky, that it wasn't really random at all. That what was happening was, and I went ahead and put a couple of them. I put Mercury, the planet closest to the sun, and I put Saturn, the most distant one, but you'd arrange all 5 in between there. That these planets are wheeling through the cosmos on essentially 2 orbits superimposed. Each planet would be doing a large circular orbit. Saturn, for example, takes somewhere around 20 or 30 years to do that large circular orbit. But then superimposed on top of that, there's what Ptolemy called the epicycles. And these are these little curlicues added to that circular orbit. And again, at first, if you're not paying attention, it just looks like those 2 motions together just give you complicated random motion. But if you are paying attention and you work out the math of if we were sitting here stationary in the center of this whole system, and if you did have Saturn, for example, wheeling through the sky in a large circle, but then with small circles superimposed on it. And again, the physical model that they had in mind for this was that there are these giant spheres of ether. Now, there really aren't giant spheres of ether, but they thought they were. That there are these giant concentric spheres of ether that all the celestial objects move on, but that the planets had a smaller sphere of ether rolling on the inside of the larger one. And the smaller sphere is what would be responsible for these epicycles. The larger sphere that the small one was rolling on would guide the planet around its large main orbit. Mathematically, it worked. If you work out the calculations, the geometry of what would you see from the center if you were looking at these spheres rolling within spheres, you would see exactly what you really do for the planets. You could use Ptolemy's mathematical model to predict where each planet would be in the sky anytime past or future for, decades in each direction, and you'd get your predictions right. So it was an impressive piece of mathematical reasoning. For reasons I'm going to show you in a moment here, I feel like this was a lost opportunity where Ptolemy could have made some serious improvements to the physical model of what was going on there. But in any case, this would be your geocentric model as of around the year AD 50. And continuing, if I made it sound like it's kind of almost an embarrassment to humanity that we had gone 500 years without a major update to Aristotle's model, well, now that Ptolemy had made his updates, we would go about another 1,500 years without a serious update to this astronomical picture. It would not be until the 1600s AD, when Galileo and later Newton were making their arguments, that we would finally start to make a serious shift here. Now, what is the alternative model that I wish we had taken the evidence and been able to seize on earlier? Well, let me take you over here and we'll find out. This is known as the heliocentric model. Again, the name tells a big part of the story. Helios is the Greek prefix for the sun. Centric, again, just means centered. So this is a model with the sun at the center. Now, am I going to say the sun at the center of the universe? No, actually, I'm not going to say that, because unlike the old geocentric model with Ptolemy, both Aristarchus and then his much later successor, Copernicus, who came along in the 1500s AD and would kind of jumpstart that revolution that Galileo and Newton would continue, they both realized early on in their investigations that if you are going to be placing the sun at the center, not of the universe, but of our local solar system, our local group of nearby objects, that the universe has got to be a hell of a lot bigger than anybody had realized. That the stars are not 2 or 3 times farther away from us than the sun. That the stars are vastly, I was going to say almost infinite, but infinite's a pretty heavy claim to make. But the stars are vastly farther away from us. Again, if it takes 8 minutes, as it turns out, for light to travel from the sun to the earth, it takes 4 years for light to travel from the sun to our closest nearest neighboring star, Alpha Centauri. A lot of the stars you see in the sky, it takes dozens to hundreds to thousands of years for light to travel that far. And as soon as you start looking at the large-scale structure of our galaxy, now we're talking tens of thousands of years. As soon as you're starting to look at either nearby other galaxies, now we're talking millions of years. So yeah, the universe is, and by the time you're talking about the structure of the observable universe today with our best instruments, we are now talking tens of billions of years for light to travel that far. So yeah, the universe is a lot bigger than anybody had realized in Ptolemy's time. Aristarchus, who we talked about coming along just 100 years after Aristotle. So he tried to make some cases that we should change those other models. Well before Ptolemy even came along and did his studies of the planets, Aristarchus was arguing that no, the Earth is not the center of the universe. Sadly, the arguments kind of fell on deaf ears until much later. But what was his model? Well, again, his model was that the sun is at the center of the solar system, rather than the sun orbiting the Earth every 365 days. It's the other way around. The Earth orbits the sun every 365 days. And also, rather than the entire cosmos spinning on its axis every 24 hours, he said, no, the only thing that spins on its axis every 24 hours is the Earth. So the Earth itself is rotating every 24 hours, which is why all the other celestial objects that we're going to be adding to these models all seem to swing across the sky on that 24-hour cycle. So that would mean the sun would rise and set every 24 hours. It would also explain why the sun did its yearly circuit against the background stars. Again, it's not that the sun is orbiting every 365 days, but it's the Earth is orbiting every 365 days. But that still means when we observe the sun at different points in the year, we are going to see it lined up with different sets of background stars. So, that would give the sun's apparent swing through the sky as the seasons go on and the year advances. The moon, meanwhile, really is orbiting the Earth every 28 days. And again, from Earth, we can see the moon swing through the sky against different background stars. Why does this require them to require, both Aristarchus and Copernicus, I think independently, came to the same conclusion that the only way this model works is if the stars are vastly distant? Well, because if I tried to put one of the background stars, say here, if the Earth were at rest at the center of the universe, that star would stay put. I mean, it would wheel through the sky in 24 hours because everything wheels through the sky in 24 hours in that model. But other than the 24-hour cycle, that star would stay put if the Earth were at rest at the center of the model. But if the Earth is orbiting the sun, then you should be able to calculate a line of sight on that star, map out what direction the star is, and then just wait a few months. The ideal time to wait would, I suppose, be 6 months, because then the Earth would be on the opposite side of the sun. So if the Earth is over here on the opposite side of the sun, as far away as it's ever going to get from that starting position over there, if I then again did a line of sight on that same star, I would find it in a notably different direction. Again, the name for this phenomenon is stellar parallax. That word parallax is just an all-purpose word meaning triangulation, meaning anytime you simply plot the direction to some object. I'm looking at the doorknob of the door over across the room right now. And then you move to a new known location. I move over here, and again I plot the direction to that doorknob. If I plot out geometrically where those two lines cross, I'll be able to tell the distance to the doorknob. Or this is also how your eyes do three-dimensional vision. This is how you have depth perception. Or this is one of the ways, not the only way, but this is one of the ways your brain uses to show you an immediate just picture of your surroundings with 3D depth perception in place, is because my left eye knows that the direction to that pen is this way. My right eye, meanwhile, sees a slightly different direction to that pin. And the point where those two lines cross, my brain just calculates, does the trigonometry automatically, and just tells me where the pin is. So if I've got like a small, fast-moving object, I stand a chance of being able to reach out and catch it. I stand a better chance with both eyes open than I would with one eye closed trying to catch the same object. These are all examples of parallax, but while a lot of parallax situations we see in everyday life, the two observation points are 10 centimeters apart for my eye, or maybe a couple of meters apart if I step over here and look at the doorknob, or maybe a few kilometers apart if I'm a professional surveyor and I observe some landmark that I want to know what side of the property line that tree's on. If I observe it from two known points on the map, maybe they're a couple kilometers apart and I've got kind of a bigger baseline and I can successfully do parallax with more distant objects. But this is a great opportunity from this moment here until 6 months later when Earth is on this side of the sun. I've moved 200 million miles. So that should be plenty of distance for me to be able to tell that that star has changed position in the sky. And it's not. When I look at that star in January and I plot what direction it is, and then I wait, I look at it again 6 months later, expecting a very different direction. I don't get a very different direction. Instead, I get that the star still seems to be in exactly the same direction it used to be. So these lines of sight are essentially parallel to each other. In other words, I don't see any evidence of stellar parallax, at least not with the instruments that they would have had available in those days. Well, what conclusion would you draw? What most of Aristarchus's contemporaries said, and what most of Copernicus' contemporaries will say in the story that we are going to tell in next week's lecture, was this proves that this model is wrong. We should be seeing, if the Earth did orbit the sun, which they thought was a pretty crazy idea in the first place, we ought to be seeing stellar parallax. The fact that we're not seeing it means no, the Earth is not orbiting the sun. The Earth is remaining stationary, and that's why we don't see any motion of the stars. However, there's an alternate explanation. What Aristarchus said, and what Copernicus would eventually independently come to the same conclusion, is that those lines are parallel. It's because that star is a lot farther away than we had ever expected. It's so far away that, no, these lines are not really parallel, but they're so close to parallel that we can't measure the difference. And that means that somewhere off in the vast distance, those lines finally meet, but we're not able to. Now, this is kind of like if I were that surveyor who's, well, again, if I was the casual surveyor here who's trying to tell the distance to that doorknob, I can plot the direction to the doorknob, step over a couple meters, plot a new direction. It is slightly different. But if I were, instead of the doorknob, if I was looking at something that's, a boat offshore down on the Monterey Bay there, I would notice a much smaller discrepancy. Unless I had really good instruments, maybe I couldn't measure that parallax shift at all. If I'm looking across the Monterey Bay at a lighthouse on the other side or something, again, unless I have exquisitely good instruments, I'm not going to be able to measure that parallax shift. Certainly if I'm looking at a star in the sky and I step sideways 2 meters, I'm not going to be able to measure that parallax shift. So if even this 200 million mile shift from where the Earth is in January to where the Earth is in July, if that's not enough to measure any detectable shift in the position of the stars, then the stars have got to be vastly distant. That is the conclusion that Aristarchus drew. That is why I consider him one of the best astronomers of that age, is because he did have this willingness to rethink his models in the face of new evidence and to improve them, as it turns out, because the stars he's right, the stars are vastly distant. By the way, by about 1840, so just almost 200 years ago today, finally telescopes would have improved to the point where, at least for a few of the most nearby stars, you could finally measure this stellar parallax shift. And it did work, and for a couple of generations, this was the one and only way that humanity had of measuring the distance to stars outside of our solar system. I will then tell you about the work of Henrietta Swan Leavitt right around the turn of the 20th century, right around the year 1900, and she was able to crack a way to measure the distance to stars, even if they were much too far away to get a good parallax measurement, no matter how much better the instruments got. So I'll tell you about Leavitt's work as we get toward the 20th century. But yeah, in any case, so the fixed stars are not part of our own solar system. They're not twice as far away from the sun. They turned out to be these vastly distant objects. But again, Aristarchus was aware of that. Copernicus would be aware of that. By the way, where would they put the rest of the planets that make up the solar system? Well, unlike Ptolemy's model that we were showing you before, where the planets move on these crazy epicycles, Aristarchus would not even attempt to try to make sense of what the rest of the planets were doing. Just like Aristotle, he just thought they seem to just be moving at random and doing their own thing. I don't get what the planets are doing. Copernicus, though, would realize that the planets are, well, it's a much simpler motion than you had in Ptolemy's model. The planet, I'll do, again, Mercury, the closest planet to the sun. By the way, this is not at all meant to be to scale. None of this is meant to be to scale. But Mercury, rather than a circular orbit festooned with curlicues, epicycles, Copernicus calculated that Mercury seemed to be doing just a simple circle. Now, later observers such as Johannes Kepler would be able to refine that and say it's not quite a circle, it's actually an ellipse. It's a particular mathematically defined oval shape is what an ellipse is. But at least by Copernicus' first attempt at the model, all the data seem to be telling him that Mercury's moving in a perfect simple circle around the sun. So is Earth. So are the planets farther from the sun than Earth. Mars, Jupiter, Saturn. So you'd have Mars out here, moving in its own circle. By my scale, it barely missed skimming the moon. Again, the scales are very different than that. But you had Mars moving in its own circle. I could put Jupiter on there, Saturn moving in their own circles. I'm not going to put all of them. There'll be Saturn, decorated by its rings, so you know it's Saturn. Hey, by the way, they didn't know at this point in history that Saturn had rings. It actually takes a pretty decent telescope to be able to resolve the rings of Saturn. But I'll give it rings for sentimental value today. But in any case, yeah, in Copernicus' model, all of the planets seem to be orbiting in a perfect circle. Well, if they're orbiting in a perfect circle, then why the hell did they look so confusing to the ancient astronomers? It looks like we ought to see them just doing a nice circular path through the sky, and that should have been real easy to figure out. The reason it wasn't easy to figure out is because as we observe them, we're not standing here at the center on the sun, practical difficulties, we burn up and everything. We're standing out here on the Earth, and the Earth itself is a moving platform that's circling the sun. That's why the planet's motions look so complicated, is we're not just seeing their motion, we're seeing their motion and kind of the reflection of our motion. We're seeing their motion relative to us, but the fact that we are moving on one circular orbit, each of the planets is moving on a different circular orbit with a different length and a different diameter. Together, that actually ends up looking like a really complicated orbit. To show you why it looks that complicated, and to also kind of show you how Ptolemy, if he had just been thinking a little more imaginatively, might have bypassed 1,400 years of history and realized the things that Copernicus realized in AD 150. Or for that matter, why anybody after Ptolemy with access to Ptolemy's data had the ingredients they needed where they could have broken that crucial puzzle of astronomy, but nobody did for another 1,400 years. But let me show you, kind of what are the implications of the fact that we are making our measurements from this moving platform, which is circling the sun? To show you that, I've got another sketch over here. Imagine, if you will, is this thing working? Yeah. Okay, imagine that, yeah. You've got a professor standing in front of a classroom full of people and entities giving a talk. So professor's up here on her podium. You got student there, there. For some reason, a cat sitting over here. The student standing still, the cat standing still. The other student happens to be walking steadily across the room in this direction. This would be a fairly calm, sedate scene of what's really happening. However, what the professor is not aware of is that some prankster in the room, possibly the cat, has programmed that disc she's standing on. It's actually kind of a giant Roomba robot. And the Roomba is smoothly carrying the professor in a circle. Aristotle would have raised the question, if she's moving, wouldn't she notice it? Eventually, we would refine that question and say the important question is not how fast she's moving, it's how rapidly she's accelerating as she moves. But if the acceleration is gentle enough, then yes, it is possible to be on board a rapidly moving vehicle and not realize it. You've probably all, driven in motor vehicles on the freeway where if it's a straight freeway, so you're not turning right or left, and if your car is going at uniform speed, you don't actually feel particularly uncomfortable. Again, there were once qualified engineers and journalists who had warned that if any human ever traveled faster than 20 miles an hour, the strain on their body would be lethal. No, it's not. It's perfectly comfortable as long as you are moving at a steady pace. You can ride on a jet airplane. Now you're moving several hundred miles an hour. And again, as long as it's at a steady pace, not uncomfortable at all. You can ride, as it turns out, on a moving planet, which is orbiting the sun at hundreds of thousands of miles an hour. And again, as long as its motion is smooth, which our planet's motion around the sun actually is very smooth, the acceleration is very gradual. So again, you don't feel any effect on it. Well, assuming that the cat has managed to program the Roomba so that it's carrying the professor around at a reasonable acceleration, she doesn't notice that she's being carried in this circle. And then as she observes the classroom around her, what is she going to conclude? Well, before the Roomba started circling, if she looked at her student over here, she'd say, okay, that student's just kind of standing there, chilling, minding his own business. Look at the cat's minding his own business. This person over here just seems to be walking a steady path across the room. But once the Roomba's doing its cycle, she looks back at the student, she reevaluates. Because now it looks to her like, again, in real life, the student's still standing still. What does the professor measure the student to be doing? She will think the student is moving in a circle. For example, as the professor's drifting to the left here at the beginning, she'll think the student's drifting to the right. And as the professor, let's say this is a north, south, east, west axis. So as the professor starts moving to the south on this side of the circle, she'll think the student is moving to the north. She won't realize it's her that's moving. She'll think it's everything else in the room. So what will she plot this student to be doing? Moving east, then north. And eventually when she's down here and she's moving east, then she'll measure the student to be moving west. So she sees the student moving kind of in a mirror image circle to the one that she's actually moving in. So again, what's really happening? The professor's moving in a circle. What does she measure? She measures the student is moving in a circle. Then she looks over here to the cat. Well, again, she'll measure that the cat is moving in a circle. What will she measure for this person who was walking steadily across the room? Well, she'll see this person still making that progress toward the west, which is what's happening in real life, but then superimposed on top of that, there will be those circles. Hey, that might look kind of familiar to the epicycles from Ptolemy's model. What if we go ahead and add one more creature to our menagerie? What if there's a bird? And what the bird is actually doing in real life is the bird is traveling in a big circle around the professor. So the bird's doing this. What will she measure that the bird is doing? She'll still see that big circle taking place, but like everything else in the room, she'll see the kind of mirror image of those Roomba circles superimposed on it. So what will she measure the bird to be doing? She'll measure it to be doing this. Giant circle with smaller circles superimposed on it. Now that is essentially exactly what you were seeing in Ptolemy's model. Ptolemy measured that each of the planets, by his calculations, were moving in giant circles with smaller circles superimposed on them. Why? Because he's standing on a freaking Roomba. Okay, it's not literally a Roomba. It's a planet orbiting the sun. But he is standing on a platform which is carrying him in a circle, and he's mistaking that for the notion that everything else in his field of view is moving in a circle. What are some clues that the professor might use here to realize that it is not the objects in the room that are doing these crazy little epicycles, but that it's her moving in a circle that kind of gives rise to all that, or that she is making her observations from a moving platform? Well, one thing she might notice is that whatever amount of time it takes her to do one circle here, maybe it's 30 seconds, she'll measure that every object in the room is doing epicycles at that same 30 seconds. She'll measure the student is going around every 30 seconds. She'll measure the cat is going around every 30 seconds. The person crossing the room, hey, they're traveling at their own speed as they cross the room, but the epicycles superimposed on that, that's going to be every 30 seconds. The bird, who knows how long it takes the bird to do that giant circle? We never specified. Maybe it takes 3 minutes or something. But how long does each of these epicycles take? 30 seconds, because those aren't really something the bird's doing in the first place. Those are echoes of the motion that the professor is doing. So, did Ptolemy have a similar clue? Yes. On this model, okay, again, what's really happening is the Earth is orbiting the sun every 365 days. What did Ptolemy measure? Well, he measured that the sun, this would be like one of the objects that was stationary in the professor's model, like the cat. The sun would only be doing that 365-day loop, but all of the others, Mercury, Venus, Mars, Jupiter, Saturn, each of these had their own length of time for the circle that ends up representing their own orbit around the sun. But the circle that was superimposed on that, the epicycle, was always 365 days. So the sun, the object that turns out to be the closest thing to a stationary object in the real model, the sun is orbiting every 365 days, but all of the planets, they've each got their own amount of time they take to do their large orbit, but their epicycles are all exactly 365 days. The other thing that the professor might notice is that all the epicycles are the same size. If, say, this is a circle of 5 meters diameter that she's moving in, then again, the bird's large circle could just be whatever diameter it wants, but the smaller epicycles superimposed on it, since those are echoes of her own motion, those will all be 5 meters in diameter. So the stationary student, the stationary cat, 5-meter diameter circles. The student who's walking in a straight line across the room, 5-meter diameter epicycles superimposed on whatever straight line they're doing. Bird who's doing the giant circle could be whatever size the bird wants, but the epicycles are 5-meter circles superimposed on top of that. This, now, was Ptolemy able to measure that the size of all the epicycles were the same size? Not exactly. his measurements were not necessarily all that accurate. I didn't realize this for many years, but when I finally got a hold of the translation of some books that survived the repeated catastrophes at Library of Alexandria and all that, and took a look at some of Ptolemy's data, he was pretty far off on what he thought the size of the epicycles were. They were all kind of in the same ballpark, within a factor of 2 or 3, or in one case 6 of each other, but he didn't measure them to be exactly the same size. Not because you wouldn't measure them to be exactly the same size with good instruments, but he didn't have the greatest instruments. So he did have the clue that all the epicycles took the same amount of time. With better instruments, if people had found it worth, just out of a sense of curiosity, following up on Ptolemy's measurements and improving them, then as the astronomical instruments got better, they would have kind of realized more and more closely that all the epicycles were the same size. Would people have made the leap to realizing that it is not the planets that are doing these crazy epicycles? We are doing a yearly orbit around the sun, and the epicycles are just the echo of our own motion. I don't know. But as it is, it took another 1,400 years after Ptolemy's original breakthroughs before we started making serious progress toward revising this astronomical model, and more importantly, toward revising Aristotle's models of physics. And they did kind of go hand in hand. A big part of the reason why everybody found Aristotle's geocentric models of astronomy so compelling was because they did, their models of physics, Aristotle's version of physics, did make this claim that if you were on board a moving object, there'd have to be some force to keep the object moving, and there'd have to be some force to keep you moving with the object. Again, right around the same time they finally shattered these geocentric models of astronomy, this was the same moment they finally shattered that model of physics. And again, realized that it does not take a force to keep an object moving. Question 6 on the homework is kind of a trick question. It does not take a force to keep an object moving at a constant pace. It takes a force to change that motion. It takes a force to make an object speed up. It takes a force to make an object slow down. It takes a force to make an object change direction. But if all you want to do is keep on moving at the same pace, the only reason that ever takes a force is if there's already some other force trying to push you off that pace. So if you say, wait a minute, when I drive my car on the freeway, I have to keep my foot on the gas pedal, otherwise my car is going to slow down. Yeah, but that's not because your car naturally slows down when it's not being pushed on. It's because air resistance is pushing it backwards, and that will make it slow down if you don't do something to counter that force. So again, the mistakes they were making in their models of astronomy and the mistakes they were making in their models of physics, it was really the same mistake both times. And if you are going to make progress toward correcting one of those mistakes, you got to kind of correct it all at once. Which is why it took a very imaginative and a very stubborn figure such as Galileo to finally break us out of that incorrect pattern. But more on that next Tuesday. For now, this is mostly what I wanted to tell you about Ptolemy's model and the alternative models that we might hope to replace it with. And I am going to record one more thing over the next day or so that is a history of the Great Library of Baghdad, the House of Wisdom, which was at its greatest glory between about AD 800 to AD 1200. And they came so freaking close to being able to shatter both the misconceptions in physics and the misconceptions in astronomy. But the glory days of that community ran out with a series of invasions that I'll tell you about. But they didn't quite manage to crack the puzzle. And again, it would be several hundred more years before before we finally started making serious progress again on this. Anyway, all of that next time, but let me sign off for now. Enjoy the weekend. Problem 6, like I said, think carefully, and I will talk to you all soon. Take care.